School for Poetic Computation here in New York City. It is Friday, March 16th. Where's the date on this computer? It's gone. Whatever, it's 17th? Oh my God, this is terrible. Here, I can look over here. I have the date over here. 18th, I knew that. It's Friday, March 18th. About 4:40 Eastern time. And I'm here, this is sort of like a last minute effort to record a video this week. I have not been able to. I've been sort of fiddling with lights and trying to get things set up, and life gets in the way. Next week, I hope that I will be having 2 much longer sessions, and I hope that next week I'm actually going to get started in doing my Git and GitHub tutorials, which I plan to do. But today I'm also more just sort of starting, doing another test here in this space. I have a different whiteboard set up here. I'm going to see how this works. I'm probably, oh, I almost knocked it over. Oh my goodness, it's very, I'm going to get one that's mounted to the wall, but this is just a test. Where's a pen? I'm probably out of focus, which I need to deal with, but maybe this is not out of focus and readable. Tell me in the chat if that's the case. I don't know if there's anybody actually watching right now. Let me go check this live dashboard to see if there is anybody. It says there are 5 people. Oh, I can see that looks pretty hard to see. Tell me feedback-wise about how that whiteboard looked. How is that? Hello, everyone in the chat. So I thought I would do, I had on my list here. I'm trying to look for like a little quick and dirty topic to do. I thought I would do, I could do P5JS instance mode actually. Just, oh, I'm over here. Sorry. I thought I would do, let's see, not, contrast isn't great. Okay. Let me look over here, see if I can improve this. I wonder if actually, I'm going to change something on the camera here for a second. That's probably a little bit better. So that looks like that's a little bit better. Like the lighting in here is not good. I need to work on that. There's all these like shadows. Let me try pointing this up and pointing this up more. Oops, I turned that off. How did I turn that off? Whoa. What did I press? Didn't press anything. Now I'm in the dark. But this might be better. Wait, I have an idea. Sorry. Trying to get the lights here. Let's put this over here. Oh, this doesn't. Oh my goodness. This is riveting for you to watch, I'm sure. This is, I need a piece of cardboard or something. Here we go. Here is a piece of cardboard. I'm going to put that over here. And see if I put this here and point that light at me from over there. There we go. There's a little bit of glare here, but I feel like that's a little bit better. Put this here. How's that? How's that? Okay, that's going to have to do for right now. Going to have to work on this. Over here, hello, I'm back over here. Yeah, I should get somebody who, oh good, people are saying it's better. Maybe I made it worse in the meantime. I should get somebody to come in here and help me, which I will. But mostly I just don't have a couple lights that I plan to have, and I don't have the right plugs, and I don't have the right whiteboard, but this will do for today. Okay, so I was going to do something called a minimum spanning tree. Let's see if I Google that. This is perfect. And let's look at the definition of this. It connects all, okay, so what is the minimum? So first of all, I'm interested if you can tell me in the chat what this might be useful for. I'm not doing my video tutorial just yet. I'm just I'm doing my prep. So, and I don't have a lot of time, but I think this will manage. So what you can see here is that a minimum spanning tree is a spanning tree of connected undirected graph. It connects all the vertices together with the minimum total weighting for its edges. So in other words, translation, if I have a whole set of points, and those points are just randomly in a window, in a canvas, how can I have all the points connected to each other And if you add up all the distances, you have the minimum distance. So you can see that here in this, like, oops, you can see over there in that image, there's lots of different ways you could connect all of those points, but the particular darker edges that are there, it happens to be a path through all the points, which has the minimum distance. Okay. Oh, look, on this page, it's even going to say there are quite a few use cases. Telecommunications company, which is trying to lay out cables in a new neighborhood. Ah, okay. That makes sense. Okay, that's good. That's a good. So this is like a computational geometry problem. So I thought what I would do is build a P5. There's an algorithm called Prim's algorithm. Let's see if we look up that. It's a greedy algorithm that finds a minimum spanning tree for a weighted undirected graph. So the way that Prim's algorithm works, I'll diagram this out when we do the tutorial. I'm just sort of talking this through to practice. Is that you could start with any random point, and you find the point that's closest to that, and then you go to the next one and you find the one that's closest to that, et cetera, et cetera, et cetera. No, that's not right. You find the one. Let me look. I don't have I have my example that I made the other day. If you start with a point and you look at the distance between all the, yeah, maybe that is right. And then it's reached. You draw a line. Or we're gonna try making this. Does this sound about right? Let's read this. By building this tree one vertex time from an arbitrary starting vertex, at each step adding the cheapest possible connection from the tree to another vertex. That is what I said. Okay, I think this is going to work. This is a very simplistic algorithm. It's not the most efficient, but it's an easy way, and it's kind of visually it's kind of fun to see what happens once you start clicking around the screen and seeing it happen in real time. So I think that, anybody have any questions about that? I think I'm going to try to just build that. The quality is good, everything's good. I'm going to try to just build this. I'm going to diagram it. I'm going to build it. Hold on, let me get P5 open. I almost want to like do it. Yes, it is. Yes, I do want to open it. Let's see here. And I'm going to save this as, I made this the other day, but I have it on this other computer over here. I'm going to save this as Prim, or minimum spanning tree. And I want to just see, I'm going to maybe get a few things set up in the code already. I'm going to look at my example because I need to have a variable called vertices, which will be an array for all the vertices. I'm going to create a canvas, 600 by 400, something like that. Or I usually do 640 by 360. I'm going to do that, and I'm just going to say background 0, or like 51, something like that. And what I'm going to do is add also mouse pressed vertices dot push. So var v equals create vector. I'm just getting this set up. And here I'm going to say at the bottom of this, so that now fill 255, ellipse v.x, v.y, 1616, and stroke 255, something like that. So every time I click, oops, I don't know what I'm writing there, vertices index I, vertices index I. Every time I run it, we'll see there's a vertex there. So what I need to do now to add to this program is connect all those with lines where everything is connected, and you add up all the distances together. So it's the least amount of cable that you need to connect all those if this were some sort of like electrical or telecommunications system. And then I'm gonna look at my solution again just to like kind of make sure, draw all the points reached, unreached. All the ones are first unreached. And then start at the first one, find the record. So you need the one that is the Reached on. Oh, for everything in unreached, find the shortest. Okay. So it's a little bit less, it's a little bit more complicated than, let's see, then for everything that's in, so I'm thinking this through. I have to be ready for this. I don't know if anyone's like, I should have just have, maybe I can get this open over here so you guys can see what I'm thinking of. P5 dot, so I made this example the other day, P5 IDE dot Heroku app.com / yeah, that should work. I made it in the web editor. The P5 has a web editor, which is a very, very alpha-y project. I need to log in. Let's see if you guys have any other questions for me or anything in the chat. People are. Somebody asked, last time you talked about summer internships but never got around to describing it. Well, somebody had asked about Google Summer of Code. And unfortunately, the Processing Foundation was not selected for Google Summer of Code this summer, so we don't have our usual summer internships. But I'm seeking other sources of funding or other mechanisms for having them. So I don't have an answer to that right now. But if you're interested, feel free to send me a message on Twitter, or if you're a source of funding for the Processing Foundation, please let me know. Okay, open recent sketchbook. I should have something in here, minimum spanning tree. Open, does this work? Open sketchbook, come on. Oh wait, maybe I have to hit OK? Open sketchbook, oh. Doesn't seem to be working. Spanning, okay, let's see. Let me do something crazy here. Boy, you really, oh wait, which is, I'm going to read off the the hash code 5695 DSF1859314030014 F2EC. Almost there, everybody. Let's see. There we go. Okay. I think there was just like some sort of caching issue. So this, by the way, is the finished version of what I'm about to try to make here. You can see that this works. And I just wanted to kind of peek at the code a little bit to remind myself how this works. I'm going to build it from scratch, though. So let me talk this through for a second. So we start with a copy of all of the current vertices. Every vertex is not one that's reached. A reached one being one that we've used already and we have a line connecting it. Unreached being we haven't connected it. So we start with them all unreached. We pick a random one, or the first one. I heard a door. I don't know if somebody's here. I should go look. I still have my mic on. Oh, hey, how are you? Good. Okay. Just the neighbor. Okay. I'm going to get to the video tutorial soon. This is the part that will actually be recorded and saved for posterity. Okay, so all of the now there's lots of, I'm hearing noise now. So all of the vertices start out as unreached except for one, and we just pick the first one, which we could pick a random one and pick the first one. And then we try to find, as long as there are unreached vertices, go through all the ones that are reached and find, okay, for every reached vertex, which is just one at the start. We'll diagram this out once I remember how this works. I should have done this before. This is a bad idea, this complicated algorithm. It's not that complicated. Let me see if there's anyone in the chat. Wow, there's still 16 people watching me try to like remember how this works. As long as there are unreached vertices, start off with a large distance. We're going to try to beat that distance. So we have a reached and an unreached. So for every reached vertex, find all of the check the distance between that reached one and all of the unreached. If the distance, got it. So this is for the case that it's only for the, I see. So here we go. Now if I click here, let's rerun this. Okay, this totally makes sense now. So here, if I click here and I click here, these two get connected, and then this one here, this gets connected. Now the issue is, as I'm going through and trying to find, and there's a new point, right? If there's a new point here, I'm about to click a new point here, I don't want to connect the last one to it. I want to connect whichever one of those happens to be closest, which happens to be this one. And same thing if I go here, you're going to see, and then those two get connected. So, okay, so this makes sense in my head now. It might not have made sense to you, but I just had to figure this out so that I could explain it from scratch. Okay. Here we go. So now I'm going to minimize this. I'm going to have this set up. We're going to talk about, I'm going to run this over here, and I'm going to hit record in a second, and I'm going to make a video which shows how to solve the minimum spanning tree. I'm just recording video tutorials. Yeah, just ignore me. This is actually live right now. Live on YouTube. It's okay. There's only 15 people watching, but it gets recorded. More people will watch later. Yeah, you can come say hi if you want. Here. See, so this here is me, and this is the code. This is the neighbor, Joe. Yes.
And I have an awesome tutorial for everyone. Understand that my codes are unbreakable. Okay, that's what I wanted to say. Thank you.
Thanks for stopping by. Talk to you later. Okay. All right, that was an exciting moment to have here happen. Okay, so I'm about to, it's good that that happened before I actually hit the record button. So now I'm going to record the tutorial for posterity, which is solving the minimum spanning tree problem, which connects a set of vertices, all connected with the least amount of, if you add up all the distance, you have the least amount of distance. Okay, and then we're going to diagram it, going to code it, and we've got this example going, and that's going to be the video tutorial. Okay. All right. Anybody have any last? This is very dangerous here. I don't know this as well clearly. Okay, but all right. So here we go. I'm gonna hit record. Hello. In this video, I'm gonna give myself a headache. I can tell already, but I'm here to describe to you a problem called the minimum spanning tree. It's a problem from computational geometry kind of thing. And I'm going to describe that problem. We're going to look at a solution to that problem known as Prim's algorithm, named for somebody named Prim, presumably. And then we'll implement it in P5.js. And as always, I will also upload a processing version of this as well. But I'm going to use P5.js to actually write the code. So first, let me just show you, before I describe to you what the actual problem is and the solution, let's just look. I have a simple example preset that's the foundation for what we need. So if I just look at the code for this example for a second, first, there's just an array, a blank array, calling it vertices, because every time I click the mouse, I'm going to create a vector being an object that stores an x and a y. So I'm going to create a vector with mouse x, mouse y, where the mouse is, and then I'm going to add that vector to an array, and then you can see in draw here, I'm just drawing an ellipse for every single one of those vertices. So if I run this program and I click, you can see here that every time I click, a vector gets added to that array, and I draw a circle for every one of those spots. So the question is, what is the minimum spanning tree problem? And this is a temporary whiteboard that I'm going to see how it works. So bear with me, please. What is the problem? What is this problem once you have these points? So let's say you have the points. And I'm going to make some random points. the minimum spanning tree problem says, how can I connect every single one of these points? Every single one of these points must be connected to another point, and if I add up all the distances, I have the smallest amount of distance. So there's lots of ways that I could connect them all. Like I could just do this, and they're all connected, but I could also have done this, and they're still all connected, and I could have also done this, and they're still all connected. And if I made these pretty evenly spaced out, so probably, oh boy, this is scary. Probably if I were to draw a diagram like this, and then if I put another one here, right? They're all connected like this, but that's probably, if I add up those distances, it's going to be a lot greater than if I connected them like this. So, and it doesn't have to be a closed shape. It doesn't have to be a continuous path. The only thing that has to happen is that every single point you have to be able to get from every point to every other point somehow. So this is the kind of application that you could probably create some kind of interesting visual art project out of, but it's a relevant, it has practical applications. For example, if you wanted to connect everything with some kind of like electricity or telephone, do people use those anymore? Telephone signal, and you only had a certain amount of cable, like what's the way to have them all connected, and you're saving the most money using the least amount of cable. And I'm sure you could come up with all sorts of other scenarios for where this is relevant. So how do you solve this problem? Okay, so there's a variety of different solutions to this problem, some of which are more efficient, some of which are less efficient, some of which do it more quickly or less quickly, but the solution I'm going to show you, is called Prim's algorithm, and it works as follows. What if we start with a random point, essentially? Let's start with this random point, okay? Now, what if what we do, and we have this, I'm going to introduce this idea of an unreached vertex or a reached vertex. So at the start, all of the vertices are unreached. There's no line connected to it. They're all unreached vertices. I can't get the telephone signal to them. And we're going to start with one single, and this is now a reached vertex. So what I want to do is say, okay, what can I connect this one to that has the least distance? So this particular vertex, I can check every other one, and I can see, and I check the distance, and this one actually has the least distance. So now I have two reached vertices. This one is reached, and this one is reached. Now what I need to do is the same thing. I need to find not just the one that's closest to this one, but the one that's the least distance between this one or this one. So in other words, if this were here, but this is a little bit longer than this, but shorter than this and this, I'm going to go in and I'm going to go ahead and connect this here. But if this one is closer than this one, I'm going to go ahead and connect this. Now I need to say, is this shorter than this, than this, than this, or this and this? So I have to check every single reached vertex against every unreached vertex and find whichever pairing has the least distance. And then that gets, and maybe right now it's this one, and all these are reached, and then maybe right now it's this one, and then maybe it's this one, and then maybe it's this one, and maybe it's this one. Now, I don't know if that's exactly right, but you can see that eyeballing it, that's probably a vague solution. So this is the problem. Now let's go and write the code to solve it. Okay, I'm coming over here. Okay, so what is the first thing that we need to do? Well, the first thing we need to do is implement this idea of reached and unreached. So I'm going to create in the draw loop, I'm going to create two new arrays. One to store all the vertices that have been reached, and one to store all the vertices that haven't been reached. At the beginning, what's going on here? Every single vertex should go in unreached. So I'm going to write a loop here, and I'm going to say unreached.push vertices index I. So this is me just essentially copying. I'm sure there's somebody in JavaScript land can tell me a better way to copy an array into another array, but one way to do it is just say, hey, let me go through everything in this one array and put it all in this other array. So at the beginning, all the vertices, right? All the vertices are unreached, every single one. Okay, come back over here. Now, I want to pick one vertex to start being the one that's reached. I need something to go in the reached array. So I'm going to say var start equals unreached index 0, and then I'm going to say reached dot push start. So I want to put, I'm sure I could, whatever, this is silly to have a separate variable. I'm going to just put unreached index 0, 0, not O. I'm going to put the first vertex from unreached in reached, just to get us started. Okay, once we have that, I need to do something else. If I'm taking a vertex from unreached and it's going in reached, I need to remove it from unreached. So I need to say unreached splice 0. So the splice function set is like delete the 0 element. Only I'm not done yet. The splice function wants you to say not just which element do you want to remove, but how many. So I want to just remove one element from that 0 spot. Okay, now I have an algorithm. I want my algorithm to go the goal of this is to get everything from unreached to reached. And unfortunately, this camera shut off because I forgot to start it at the beginning of this video. So I want everything to go from unreached to reached. So here we go. I'm going to say as long as unreached dot length is greater than 0, I can keep going. So maybe there's another way in JavaScript to test if the array is empty or not, but basically what I'm saying is, as long as there are still unreached vertices, we haven't finished the algorithm yet. So every single cycle, remember, every single cycle, we need to say, what are the reached vertices? For every reached vertex, check the distance against every other unreached vertex and find the shortest distance. So in order to find a shortest distance amongst a bunch of candidates, we always have to start with something that's kind of the record. If I was trying to find the longest distance, it would be easy. I say, is the distance bigger than 0? Then it's currently the longest distance. So the first thing I need to do is just come up with, I'm going to call it record, some like large number, 100,000. So there's not going to be any vertices that are more than 100,000 pixels from each other in a 640 by 360 window. Then I need to say for every and I probably shouldn't, no, it's okay to use I. For every vertex in the reached array, check every vertex in the unreached array. Okay, for every vertex in the reached array, check for every reached vertex, check every unreached vertex. And what do I need to do? The thing that I want to know is the distance between, and let's say v1 is reached index I, and v2 is reached index j, and I want the distance between v1.x, v1.y to v2.x and v2.y. So the core algorithm here is check every distance between every reached vertex and every unreached vertex. Now, if the distance is less than the record, then the record is the distance. So what we're doing is we're saying, I want to find what is that shortest distance. At the beginning, the shortest distance is 100,000. And the first distance is like 300. Oh, it's less than it. That's the record. Then the next one is 250. Oh, that's less than it. That's the record. Then the next one is 400. Oh, that's not the record. Then the next one is 100. Oh, that's the record. So we're doing every single one always. If we have a distance that beats the previous record, we have the record. So this is the core algorithm for finding that shortest one. But if I find that shortest one, what do I need to do? I need to store also the two vertices that are involved in that shortest distance. So I need to have, in addition to just the record, I need the reached, I'm going to call this the R index, the reached index, and the unreached index. So if this is the case, if I found that record, R index is I, that's the index from this array, and U index is J. And in fact, I could actually, instead of storing we'll do that. We'll do it with the distance, with the index. So I got those. So now you can see here, I now am storing, I've checked every reached, every unreached, found the shortest one. And once that's done, once that's finished, what happens? I need to do exactly what I did up here, right? I need to say, take the unreached one and put it in reached, and then remove it from unreached. So this is my algorithm to, I found that new vertex, remove it from remove it from one array and put it in another array. I probably could like do this all in one fancy line of code, but it's nice to have it in two. And then while I'm here, I might as well draw a line. I don't have those as global variables. That's fine. I might as well draw a line between reached r index dot x. Oh, this is going to get very long very quickly. R index dot y, and then unreached unreached index dot x. Unreached index dot y. Okay, so let's see. I don't know. Did that work? Okay, so line 45. I messed something. Oh, because you know what? I better not. Here's a problem, right? I mucked around with the arrays and then I drew the line after. So that's definitely not going to work, right? I need to, if I'm drawing the line right before I start moving them around, I should do that. So let's just see here. Okay, so we got kind of something happened, and then and then something didn't happen. What? Okay, so so let's think about this for a second. So this is the core idea. Let's review for a second. How long have I been at this? Only 13 minutes. That's not terrible. So we started with every time there's something left in unreached, we start with a record. We have two indices. We go through everything in the reached, check it against everything in unreached. Ah, look at that. That's not right. V2 equals reached. So the point of the second one is to pull something out of the second array. That's clearly not going to work. And yeah, this looks like it's working. Look at that. And I don't like the way the lines look here, so I'm going to say stroke 255, stroke weight 2, and here. And you can see, there we go. We have our minimum spanning tree as I add points. And conceivably, by the way, if I wanted to just demonstrate this in a different way, I could say, I could just add like 50 random points right when the program starts. And I could say random just width, random height, and do this. You can see every time I run it, we get a new. And the one thing I'll mention about this is I'm doing, in this program, you notice the whole algorithm is happening in draw. So it's recomputing the minimum spanning tree over and over and over again. It doesn't need to do that. But conceivably, if the points were always, every time you add or subtract a point, you would need to recompute it. And so you might be, if you were using this in something, you might be more thoughtful about only recomputing it at a certain point. The other thing I'm not doing here is this particular drawing is just sort of drawn and I can't do anything with it. So if I wanted to go further with this, I would probably make edge objects. So in other words, I might have an array of points or vertices or like a vertex object. I'm just using the P5 vector object with create vector. But then I might create these edge objects so they're things that I could animate or change color and put those in an array as well. And the place that I would do that is right here, right? Instead of just drawing a line. Like I just said, I figured out the vertex. I'm just going to draw a line there. I could actually create that edge object. All right, so this is pretty much the end of the video. I'm actually going to look, though. I don't know if people are posting questions. I have this, even though if you're watching this, you might be watching this like 10 years from now. I actually am recording this live, and there are some people watching this live. So you could shut this off now if you want, but I'm going to just look and see if there's any questions. Somebody points out that, okay, there are two improvements that are pointed out in the chat, which I'll mention. Let's see if they still work. So first, I just want to make this with just 20. So one is that I could copy the array by saying reached equals unreached, the JavaScript function concat, which I guess is like concatenate. No, but then that doesn't, it's not an array, it just joins them. I'd have to then split it or something. Reached push unreached shift is another way to put the first one in. So there's all these other array functions But that one's not going to work. I'm sure there's another. Somebody will put it in the comments. Read the comments. I'm sure it'll be fixed in there. There are all sorts of other kind of array functions. Is there anything else I'm missing here? I think we did it. I'm going to post this code, a link to this code. Please post your questions in the comments because I don't know how well this was explained or if this makes any sense at all. But I'm glad to have made a video today on Friday. It's 5:15. I got to go. Let me just look. Is the code available somewhere? Yeah, the code, someone asked, the code is going to be, there'll be a link in the description. It's not available yet if you're watching this live. I'm going to stop the recording and then talk to the live people. Okay, bye. Thanks for watching this. Okay, so I've got to go. The live chat, yes, the code is not currently available, but I'm hitting save on this, and I will go, I'm going to post it later tonight when I post the video recording. If you want to find it now, you can actually go into this particular URL. You're going to have to probably pause, take a screenshot of that. But I do have a version of it at that URL that's up top that I did the other day. Okay, any other questions? That's okay, sorry about Concat. It was a good idea though. Does anybody have any other questions they want to ask? I'm going to poke around here and see if I have any other notifications, any Twitter questions. Okay, I'm hoping that this one will that people will find my YouTube channel with this particular video because I feel like this is kind of like a minimum spanning tree kind of thing that people would search for. All right, thanks. I'm going to be back next week, Tuesday, hopefully, Friday, hopefully, maybe Thursday. I'm going to hopefully do a bunch. Once I get a new whiteboard in here, this whiteboard wasn't the best solution, but it worked hopefully for today. Once I get a new whiteboard in here and get the lighting better, I will be back, and I'm going to hope to do some Git and GitHub tutorials. Okay. What's the best way to contact me about a question? YouTube comments, if you have a question that's related to one of the videos, I always try to answer them there. Twitter is fine, but if you have a complex question, what I often suggest is posting a question to forum.processing.org. If it's P5JS, there's a P5JS category, and then you can tweet me or email me the link. That way, I like to answer programming questions if I can in like a public forum, just so you know there's like a record of it and it helps other people too. But my email address is on like my website. It's daniel@schiffman.net. Oh, I'm not. You can't even see me. This whole time I've been talking and you couldn't see me at all. But hopefully you heard that. Okay. Twitter is @Schiffman. Okay. Thanks everybody. I'm going to hit stop now, and I'll be uploading the 17-minute video chunk soon.